Hi guys, my name is Furkan. I'm the co-founder and CTO of Bebo, and today we're going to be talking about how we handled growth and managed the thousands of servers. And really, it was Johnny. Johnny joined us after he graduated from 8th grade, and he basically kind of slowly got started learning some languages and things like that. And earlier this year, we went from 2 senior ops guys down to 0, and we turned to Johnny and said, "Hey, Johnny, you want to learn ops?" And right in the middle of our scaling and our growth, he's like, "All right, let's go." And today he's going to tell you about how he did it and kind of what some of those processes were about.
Awesome, thank you. It's working? Yeah. First of all, hi, I'm Johnny, as Furkan just mentioned. I'm 16 years old now. I started when I was middle school. It was a few years ago. I'm actually not allowed to be in a casino, so I was escorted here for this talk. And
Johnny, try to put the mic closer.
Closer?
Yeah, there we go.
I was escorted here for this talk, and I'm being escorted right out after, so I'm going to talk slowly, get all the details in. As Furkan mentioned, I'm the Director of Operations for Bebo. I'm very proud of that fact. It's been a few months, and I'm going to tell you what that means for us. A little bit of backstory on me. This was me in 8th grade. This was right when I started. I was just a little kid. I got a summer internship with Bebo after reaching out to the CEO. And I went through a fair amount of a learning curve. I started making very basic HTML, JavaScript, little web apps for the company, but quickly moved into working on our Node.js backend, learned Python, Golang, Java, all these other things, scaling up, becoming a developer for them. And then, of course, sometime later, our 2 senior ops engineers left the company, and we were left in a state where we didn't have anyone. So Furkan turned to me, and he asked me this question. Hey, Johnny, you want to be a sysadmin suddenly? Terrifying question. I knew nothing about the space, had no idea what I was going to be doing, but I said, sure, why not? I'll figure it out as I go. That's what I've done so far. So we're a streaming company. We ingest video, and that means that the metric that we quantify ourselves on is the amount of minutes that are streamed on our platform. So this is a chart of our growth in that metric over about 3 months. And you can see straight up, it's rapid growth. We went from 0 to a little over 1 million stream minutes every day. In less than 3 months. And then this part right here is where I joined. So I joined just when we were on the uptick, became ops here, and had to deal with this enormous scaling up of our company. This was the issue. I'm going to talk to you guys today about how I fixed this, how I managed this. So I mentioned Bebo is a streaming company. We quantify ourselves based on the amount of minutes that are streamed. What's that actually mean? What's our product? Our goal is to bring esports to every gamer. Esports is this lofty field that we see of professionals who play video games and make enormous amounts of money off of it, streaming their video. But the majority of gamers, the lower tier, can't actually access that. It's not something a normal person can do. So we looked at things that we've done in the past just as people. When I was a kid, I played soccer. When Furkan was younger, he was in Little League. And that was such a fun experience. That was what sports are to us. It's this like recreational league. You're with your friends. There's no stakes. There's no money, but it's just kind of fun. And we want to bring that to esports. So we want to bring recreational esports into the world. And the key there is that social competition. The thing that makes competition fun is having a rival, in my opinion. It's seeing someone, you're great friends with them, but on the field, you're going to ruin them. And we want to bring that into gaming. That's totally present in gaming, but what's a way we can bring that into the competitive scene for younger people and for not just younger people, but less experienced people? So our thesis here is that social is a big part of competition. The reason competition is fun is you have someone you're competing against. It's a league, you're competing against other people, you see yourself grow and you bring others down at the same time, it's fun. And the way we provide that in Bebo is through video. Video is the glue of our product. it's one thing to play a video game and know that, oh, someone on the other side of the world is playing a game too, and your scores are going to be matched up or something. You don't really care as much. But when you can see the person, when you can see the person you're competing against in real time, live, I'm playing this person right now, and I'm winning or I'm losing. They can make fun of me. I can make fun of them. That's a total social experience. That's really fun to feel. So video is the glue. If video is the glue, we need to talk about, from the engineering perspective, how do we ingest this video and how do we deliver it? We need to both take video in from every competitor and then stream it out to multiple viewers, potentially. So the way at Bebo we think about problems is, the first thing you always have to set out is the requirements. Before you even start thinking about what it's going to look like, decide what are you trying to solve. Because once you have that down, you can build the right product. So what are the requirements for ingesting this video? The first of them is it has to be very low latency. We quantify this as 50 milliseconds or less, end to end. That's crucial for us. I'll talk about that more in a minute. The next thing, ingest requirement, is that gamers are everywhere. We have users throughout the United States, all throughout Europe, a giant pool in Korea, and then Latin America as well. But they're really global. So if we want someone in Korea to be able to fight someone in North California or Carolina, we need to have super low latency, and it needs to be everywhere. Next thing is that gamers, when they just play for a long amount of time. I don't know if any of you are gamers, but when I play for hours and hours and hours on end. And that's kind of the norm. So we need to be able to handle not just a lot of video, fast, from everywhere. We need to have it super stable. You can't lose that connection at any point. So I'm going to dig in on some of these now. Latency. Why does low latency matter? It really has to be less than 50 milliseconds in our case. The first reason for that is that we do live tracking and scoring via computer vision on the video. So the video comes into our servers, and we use computer vision to detect in-game events, and we use that to score who's winning in a head-to-head match. Furkan gave a talk about this here back on Monday. If you want more details, you can watch that. I'm not going to go too deep into that part of our stack because we have so many more other interesting things to talk about. But for that reason, it has to be super real. If you are playing a game and minutes later you get your score, it really doesn't feel live. It doesn't feel like you're head-to-head. It's not quite as fun of an experience. And that low latency, crucial for this live playing experience. When I'm playing a game against someone and we're in the same room, I can kill them in the game or beat them in whatever we're playing, and I can see them go, I lost. You can see an immediate reaction. There's no reason we can't do that over the internet as well. That's where the world is going. So recreating that live playing experience is absolutely crucial. This is a screenshot of a very popular game. I'm sure many of you recognize, Fortnite. And these are the pieces of information that we actually grab from that frame and use to score. So you can see on the bottom there's health. There's 2 health bars. We need to know those so we can kind of tell where you are, how close are you to losing or dying. There's your inventory, which is what items do you have, how likely are you to beat the other person given the items that you guys both have. And then there's some game stats. So that's how deep into the game are you, how many people are left, how many people have you killed, stuff like that. That lets us overall figure out how you rank as a player and match you with other people who are at the same skill level and predict who's going to win. This is a graph or a diagram of all of the regions that AWS is in as of a few days ago. It's also a diagram of where all of our players are. We're in every region available to us because we need to be close to these people. We're everywhere. Every availability zone in every region. So I mentioned that when you play for long amounts of time. I want to quantify this a little bit. The average game session on our platform is well over 3 hours. That's 3 hours of continuous video being streamed that we can't have an interruption during. Now, that's the average. There's definitely a lot of outliers that are going up into the 8, 9, sometimes even 10-hour range. And that's a long amount of time for you to maintain a single video stream. So stability is crucial here. And with that stability comes the knowledge that we have enormous spikes in our traffic. One thing that we do is we run synchronous real-world events. So these are tournaments. We know when these are happening. And we know that every time we have a tournament at 3, say, at 2:30, we're going to see an enormous ramp up in users because everyone's getting ready for the tournament, everyone's coming online, and then right after the tournament, everyone will drop off. Our traffic patterns are enormous, enormous spikes. The other thing about that is many of our audience are kids. They're in school. It means that for the majority of the day, they can't play video games. They can't play video games at school. But at 3:10, school gets out, everyone heads home, boom, immediately. Everyone's getting online, everyone's playing Fortnite, and we need to expect that enormous spike. So we need to be able to handle spikes in traffic without compromising the stability of our platform. And then lastly, gamer rage. It's become a hallowed name in our company because gamers get very unhappy when something breaks in the middle of their game. A lot of times, like I said, they're in these real tournaments. You're in the middle of a competition, you're head-to-head, you're second or first place. If suddenly you look over and you see that Bebo broke, your points aren't being counted, and you lost because of that, you're furious. And gamers are all about getting in the game, and they're super high energy, super high excitement. So this rage amplifies very fast. You never want to make a user unhappy, but with gamers especially, they get very, very unhappy. So with all these problems in mind, what did we do? The first thing, well, once we have a problem, you got to make a solution. So the first way we did this was we do the ingest of the video and the video detection on the edge. So we don't send all the video to some central region where we process it. Every region has edge locations that ingest all the video there and do all the detection on the region. The next part that we had to build was automated scaling. So we don't scale up or down as humans for these tournaments or for these expected spikes at the end of the day. We have software that does it for us. And I'll talk about that more in a little bit, but what this software essentially does, it's going to bring up new instances when we expect or are in the middle of high traffic, high load situations, and then it will quickly ramp down because otherwise we'll be stuck at these high marks and be wasting just money. And the last thing, and this ties into the stability part of it, is we need to have direct connectivity. When you have these long-running streams, any additional hop in the network layer is a potential case for failure. So we connect users directly to the box that is ingesting their video. There's no proxying or anything, which allows us to maintain longer, higher quality streams. So I've set out this what the problem is, what the solution is. Let me show you what it actually looks like. So here we have a challenger. They're playing a game, they're streaming on our platform. We use WebRTC as our video communication framework. So WebRTC stands for Web Real-Time Communication. It has a bunch of benefits. It's usable in a bunch of different scenarios and delivers high-quality video very fast. And we ingest this video on the server using GStreamer. GStreamer, again, amazing, amazing tool. It's a video framework that builds pipelines, and it's incredibly extensible. We use it for a bunch of different things on the video side, and it's an amazing tool. Let's leave it at that. And once GStreamer has this video, we do the detection by sending it to SageMaker. So GStreamer takes 1 frame every second of normally a 60 or 30 frames per second stream. And it takes this frame, it's an image now, and it sends this frame to Amazon SageMaker, where we do detection to tell, oh, did a kill happen here? Oh, did you die here? Oh, did some other event happen? Like maybe you're in some special place, we need to do some other action. And it sends all this data into the rest of our stack to contribute to our scoring. While the video is streaming, we actually want to keep that video around. So asynchronously, we take this live video and we chunk it into 2 to 3 second chunks. and we ship that to S3. The reason for this is in the future we might want to show that video. Players, after they play the game, might want to watch how they did and watch how their opponent did. And shipping it straight to S3 in these chunks allows for immediate HLS streaming. So we have the live component, and then we have immediate history, so we can watch it in the future. One of the other beauties of using WebRTC and GStreamer together is it's not just where you can push to, you can actually pull from it as well. So if you're playing a game and your opponent wants to watch your video, they can pull directly from GStreamer using WebRTC and display it in their app. And this is not just one viewer, this is potentially end users. And it's super light on the server because this isn't decoding and re-encoding the video. It's actually just relaying it through within WebRTC and GStreamer. We've gotten pretty high quality using this. We can consistently do 1080p, 60 FPS streams, which is on the upper end. We wanted to use 4K, haven't quite gotten there yet, but 1080p 60 is our average video quality. So let's talk more about this inbound video. WebRTC, I've mentioned it a few times, but it's an amazing tool. One of the benefits of it is that it's a web framework. What this means is that it's not just, we can use it in the browser. We can also use it on mobile, so it's supported in both iOS and Android, most modern browsers. We can use it on consoles. A lot of gamers don't play on PC. They play on Xbox or PlayStation or some other Switch, I think is here somewhere. And they all support WebRTC, so we can actually do the video encoding and sending using this one framework across all these different platforms. It's also on desktop, so we use it in a desktop app that we've built. And it's beautiful because we can just use the same code base across all these different systems. I referred to GStreamer earlier as our video framework. I'm going to call it here actually our video router. It takes in all this video, and the beauty of it is that it's incredibly extensible. So we've built custom GStreamer libraries and plugins, and all these things on top of it that allow us to do all these things that we want with video. The splitting off into WebRTC back, into S3 chunking, and to SageMaker all happens in one pipeline. It's an incredibly useful tool. It's open source too. You should check it out if you're interested in video at all. And lastly, we went with TCP-based video. This is somewhat of a different decision than most people. Most people use UDP video. The reason we went for TCP in this case, which is supported in WebRTC, is we noticed slightly longer latency, but it's possible that the benefit of TCP is that when you drop a packet or there's an issue sending that video, we can retry, and the video doesn't stutter as much. So we generally saw better video quality using TCP. Talked about getting the video in. Let's talk about sending this video out to the different places. So I've talked about this viewers pulling this live feed. The beauty here really is this relaying. So we used to, before we used WebRTC, we went with an RTMP-based approach, and we had to decode and then re-encode all the video on the server. There was a major issue with this. First of all, that the video quality got lesser every time. And second of all, it was really heavy on the CPU of the box. We could have maybe 1 or 2 people on an instance. And when you have thousands expected during peak hours, you can't do that. You can't have you can't have 2 people per box and thousands of boxes to maintain any cost efficiency. Since they can pull it though, WebRTC, it's relaying and it's much lighter on the client. And it's real-time detection. This is very much real-time. I don't remember the exact latency stats, but it's in Furkan's presentation. The end-to-end, you send this video up from the client, the person gets a kill in-game, and then you see the action in the app very fast. And SageMaker allows us to do that. It's a great tool. And then this async recording for the future. So this is the 3 places we send the video out to for different reasons, all through the beauty of WebRTC, GStreamer, and some smart engineering. So we've laid out a pretty good design. It's pretty solid. I've gone through a fair amount of the requirements. How do we actually make this happen? So what does it look like in our production environment. The first thing we're going to talk about is we made this project called Stark. This is my child. I love this project. It's the biggest thing I've worked on for the past couple months. And it's our autoscaler. So this is that project that will scale instances up and down according to use. And we built this custom. So again, when we're thinking about how to fix a problem, we got to talk about what are the requirements here. So the requirements for Stark, the first of them is it has to be 100% automated. 100% robot, 0% human. We echo that phrase a lot. The reason for this is when we first started, it was 99% robot. We had systems like that and 1% human. Every once in a while, someone would have to go in and type a command and make a process go all the way through. But I realized if you're doing that once a day and you have 100 users, suddenly you get to hundreds of thousands of users, it's taking more and more of your time. Anything that a human does, essentially, a robot will be able to scale much better. Anything that's human, we have to remove from the entire process. We went super deep on this. In fact, there were times that we would bring up a whole system. It would be an entire VPC or an entire region. It would take a lot of time. It would be 100% automated. And at the very end, there'd be one little thing that's different. I would have to SSH onto a box, run a command or something. And if I had to do that, I would delete the entire thing, start over. If I have to do that human action, it's wrong. We need to make that a robot action instead. The next thing that Stark does is we do velocity-based autoscaling. This is a really cool feature that I'm very proud of. Basically what it means is that we don't go off of how many users are on. We go off of the rate of change of how fast are users joining. So if we normally have, say, 100 users joining in an hour, if we notice that suddenly there's 200, 300, 1,000 users joining an hour, that means not only obviously our load is going up, but we need to overcompensate for the next, we need to overshoot for the next iteration. So we'll bring up even more than we think we need, just in case this continues. And this goes both ways. This is predictive as well. So we look over past history. We look at, at 310 every day, we have these spikes. That means at 310 every day, or at 3 every day, we should start scaling up. And we see, every day at 5 or 6, their parents realize they're playing Fortnite for the past few hours. The kids need to stop playing games. They go do their homework. We have this giant drop-off. We can analyze this, and Stark will analyze this pattern and notice, at 5, we can start scaling down a little bit more aggressively so as to save money. And last thing is problems need to fix themselves. Since we're in 15 different VPCs, if there's a problem in multiple and someone has to go in and fix it, if this is happening multiple times a day, if there's happening late at night, someone's not around, a problem can't just happen. So the way we design Stark is that it needs to be able to take issue boxes or issues in our architecture and compensate for them. I'll talk about that more a little bit in detail in another slide. So there's a few constraints that we had while thinking about how do we build Stark. We always need an available server. That means we can never be under-provisioned, ever. If a user tries to stream, if the user tries to use our app, and they see loading, or they play, and they see that their kills, their score didn't track, that they're very unhappy. And this ties back to that gamer rage I was talking about earlier. They're infuriated. We can never have not enough servers. Live video is very fragile. So we can't accidentally scale down too heavily. If we accidentally stop an instance that has video going to it, the connection drops. It's hard to reconnect that without any issues. They could have some killer play. One of the biggest streamers could come online at that moment and get 20 kills, some crazy thing. And if we miss it because we scaled down too fast, we're going to be in trouble. And lastly, and this is kind of a softer constraint, this was only me. We had one engineer on this, which meant that we had to do it right. We had to figure out all the problems on the onset, and we had to have this automation. We had to make this code deployable. We had to have good revision history. We had to have tests. There was very little leeway. So this is the overall bird's eye view architecture of Stark. It lives on an EC2 instance within a VPC, and it manages 3 different states of boxes. The first is healthy. These boxes are healthy boxes in AWS standards, so they're running in the AWS EC2 console. They're passing all their status checks, and the actual service health check is passing as well for the instance. Next is full. Our instances report how full they are, if they can take more load or not. And if they're full, we don't want to route traffic to them. We want to categorize that as a separate type of box. And then lastly, unhealthy. For whatever reason, these boxes are not happy. They're not playing nice. Maybe their service health check isn't passing. Their load on the box CPU is too high. They're not reachable in AWS. It could be a number of things, but whatever it is, these are the three types of instances that we need to think about and care about from Stark's perspective. So what exactly does Stark do in its normal iteration? The first thing it's going to do is it's going to fetch the EC2 and the health state. This consists of a Bebo3 describe instances call, as well as reading from an external data source as to the service health check. I'll talk about that more in a minute. Next, its main goal is route traffic to healthy instances and only healthy instances. Healthy instances mean I can take another user. I can do more operations. If it's not that, we don't want to send more traffic to it. And last, manage scaling logic. If a healthy box goes to a full state, we need to bring up more healthy boxes. If a full box goes to a healthy state, then we're going to scale it down a little bit. We have a little bit more than we need. So what this looks like in a workflow, the actual workflow that Stark goes through, looks like this. We use etcd, which is a database, a key value store with watches and some other nice features. And we store all the the service health state in that database. Stark reads from that, and that's how it determines how healthy an instance is. And then it reads from the AWS APIs. This mainly consists of EC2, but it also is Route 53, as Stark manages the routing and creates and deletes DNS records too. It's sending all this information into Stark, and once Stark has it, it's going to do an action. It's going to do an action to EC2 or Route 53. In EC2, this would mean starting up or stopping or terminating an instance. In Route 53, this would mean creating or deleting a DNS record. So I mentioned that Stark gets this EC2 state information, but what's the actual information that we care about here? The first is its state. So this is it running? Is it stopped? Is it terminating? We need to know this. Obviously, we don't want to route traffic to a box that isn't even running any code. That doesn't make any sense. And then the minutia here is that there's appending states. We need to know if it's going from if we're creating a box. We need to know if we're stopping a box. The reason this matters is when we're doing our logic, it's possible for an instance to take more time than one iteration of Stark will take to complete its action. There's an inherent race condition there of if you start creating 5 boxes, and then the next iteration you see, oh, there's no boxes that are healthy. Create 5 more. Next iteration, oh, create 5 more. Suddenly you've 3x how many you actually want to create because you're not compensating for the boxes that are in the middle of an action. They're pending. And this applies between all state changes in EC2. And lastly, there's some meta information. We need to know the public IP address and the private IP address of an instance. How else are we going to create DNS records that route to it? We need to know some tags as well that we put on the instance that tell us what software is running and other information that we use there. Once it has this EC2 state, we need to determine the actual health of the instance. The way it does that, we run all of our code in Docker containers, and we leverage the Docker health checks on the instance. So Stark will pull the Docker health checks of every instance, of every container running on every instance, and report a full state. This gives us not just is it healthy or not, this gives us some more information. So capacity and load, how full are we? Can we be stopped? Some services, they can be stopped even if they have a user on them. They'll reconnect perfectly. There's no problem. Some can't. We want to leave that in the application realm. They can decide decisions like that. And then we take these EC2 status checks in, and we merge these 2 pieces of information. If either one of these is failing, if the box is terminated, but status checks are reporting healthy, it's an unhealthy box. If a container isn't running that we expect to be, but the instance is running, it's an unhealthy box. And then lastly is DNS reachability. Since Stark creates DNS records pointing to every instance, we monitor these DNS records and ping them to make sure that we can always get in contact with every instance. If we can't, again, on any of these three, that's an unhealthy case. We need to mark this box as unhealthy. So I mentioned a few times, Stark does routing. It creates DNS records. There's 2 layers of routing we do. The first of them is we do latency-based routing to the region. This is a feature in Route 53. Highly recommend. It's a great feature. But it basically means that we'll create a DNS record pointing to a set of instances, and Route 53 will handle the latency-based routing to make sure you get to the closest possible region, closest possible availability zone via latency. Once you're routed to one region, there's a random multi-value feature in Route 53 again. We leverage a lot of their tools. And that will make sure that we route you to a different box. We don't want to have 10 people go live at the same time, and they all go to one instance, and that instance gets overblown, and it goes down, and suddenly they're rerouted to different instances, and we just have this collapsing effect across the entire region. We need to make sure that we load balance randomly is how we do it. We need to do this. We need to also be doing direct connection. So we're doing this without any proxying. This is all via DNS and Route 53. So I'll show you now kind of how that looks from the DNS perspective. So the first thing we're going to create is we're going to create a v.bebo.com A record in Route 53. V here is for video. It's our ingest record. This is where everyone is going to stream their video to. When we have video ingest servers in US West 1, we use the AWS short names in our naming schema. So this v.bebo.com creates a latency-based record to usw1v.bebo.com. This means anyone in North California will route here. Because there's no others at this time, everyone will route here, though. And then this usw1v.bebo.com is a multi-value answer pointing to different instances. In this diagram, there's only one healthy instance. There could be as many as you imagine. And we name these instances off of the short name, the type of instance it is, and then the timestamp of when it was created, .bebo.com, as that is our website. So what happens when you create a second region? Say we spin up servers in Latin America, SAE1, Sao Paulo. We create SAE1v.bebo.com. We have that pointing as a multi-value answer to the one healthy instance that's there, SAE1v5678.bebo.com. So say one of you is here, we're in Las Vegas, and you want to use our platform. We have this person in Las Vegas. What's the path that they go to get to a server? They're going to go this way. So they're going to connect to v.bebo.com as their video ingest endpoint. That's going to route them to the closest location. Las Vegas is closer to California than it is to Sao Paulo, unless you have some very strange network conditions. So you're going to be routed to US West 1. Once you're there, you'll be routed to the one healthy instance. And since each of these is DNS only, this is only one connection. This is direct connectivity straight to the box. So once we have instances, they're healthy, we know how they're healthy, we know how to reach them. Some of them are going to start getting full. We're going to have users connect to them. We need to actually scale up or scale down in that case. So how does Stark do the scaling? One thing we noticed while building this is that creating an instance takes a lot longer than it does to start an instance. In our tests, we saw that being a difference of as much as 2 minutes versus 10 seconds. Taking 2 minutes to scale up, in our case, is not an option. We have users coming on. Not being available for 10 seconds means that you're losing up to 100 users, potentially. 10 seconds is a much more reasonable benchmark, and we can, due to that velocity-based scale-up, we're kind of prepared before as well. So how do we fix this? There's 2 parameters that Stark takes into account when it does its scaling logic. The first of them is the minimum healthy. This is the core pool that Stark is trying to keep of healthy instances. This could be 1, it could be 2, it could be 4, it could be hundreds. But this is how many Stark is always going to make sure it keeps this many healthy instances ready for users to route to. The second param is a little more interesting. This one's min stopped. This is how many boxes we're going to keep that were healthy, but then we stop them. The reason for stopping them is they're a lot cheaper. We don't pay for the running hours. There's still some overhead of like disks, and there's a small amount of cost, but they're much cheaper than healthy instances that are running. We can keep this around as a reserve pool, and they're much faster to start. And once they start, they'll immediately go into a healthy state. So using these two parameters, we can adequately configure a cluster to always have healthy instances, and then in rare cases where we have large spikes, or in our case, very common cases where we have large spikes, we can compensate. And last is velocity-based scaling. I think I mentioned this a little bit before, but this is one of the most awesome features of Stark. This is this rate of change feature. And this has the predictive scaling built into it. Between these three features, we have next no downtime. I'll give you some exact numbers on that at the end of this. So now this is how we talked about earlier. There's the healthy, the unhealthy, the full. We're going to add in the full and the stopped instance into this diagram and how Stark thinks about them. So if there's a full instance, say there's 2 in this region, that means that Stark isn't going to route any traffic to. It's going to delete the DNS records that point to it. Then there's 4 healthy instances in this example. These ones are happy. It's all green, all smiley faces, everything's great. Traffic's going to be routed to them. This doesn't mean that they're empty. It's not full versus empty. It's kind of a thing that we had to get over in our heads. But some of these boxes could be 60% full, but they're reporting that they can still take on more load. Then there's these pending instances I talked about. They have a 2-minute timeout. So if a box we've said to create a box and it's taken more than 2 minutes, something's not quite right with this box. Or if we've said to stop this box and it's taken more than 2 minutes, this is unexpected. This is an outlier. This is not something we want to have in our stack, which is designed to be very real time. So if it's more than 2 minutes, we just terminate the instance. We delete DNS records, we make sure it's completely gone. Then there's this stopped pool. As a baseline, we keep half of the healthy number around. This obviously changes via velocity-based scaling. In some cases, this will catapult way higher. And then it's also configurable if you need a different baseline, because different clusters need different things. And lastly, there's these unhealthy boxes. They also have a 2-minute timeout. If a box cannot become healthy within 2 minutes, straight to the chopper, terminate it. So some details on how Stark is created, how it's written. It's written in Python 3. It uses the Bebo 3 SDK to communicate with EC2 and Route 53 AWS APIs. It runs in a Docker container. All of our code runs as Docker containers. Big fan of Docker, Bebo. And it's installed by Terraform in every region. Terraform is a great tool that we use to bring up our regions automatically. So this is how we automated this region this region creation process. And it's the only thing that Terraform really does is create an instance, install Stark on it, and let Stark run. Stark brings up some of the rest of our architecture. I realized I was confusing. It brings up all of it, the sum. So how did we do? We've been using this for a few months now. Stark manages not just our video ingest, but all of our architecture across our dev, staging, and production environments. So how's it go? Let's see some results. Right now, we ingest 30 terabytes of video every day. This is across 15 regions, and this is our daily ingest via this strategy. This is, for us, a fairly low number still. We want to scale this up quite a bit more as our company grows, but it's not an unimpressive metric. We're in 15 regions worldwide. I believe that's all the ones that are available to us right now. barring maybe one or two. And we'll go to more as more gamers pop up there. And lastly, we've had an 83% cost reduction by employing Stark in our stack. Previously, we had different auto-scale software that we've gone through a few different iterations on. We had humans predicting, oh, we know that a tournament's going to start at 3. Let's scale up at 2:30 manually. People would forget to scale down afterwards. We'd waste exorbitant amounts of money every day. But by using this automated infrastructure, we're able to achieve all of these results. In terms of connectivity, so this is this DNS, routing, Route 53 stuff I mentioned earlier. We have around 50 milliseconds of latency for the vast majority of our users. This is greater than 94%. Of course, there's always some weird person who's in the middle of nowhere, barely has dial-up or something. They have more than 50 millisecond. And this is 50 millisecond end-to-end. So that's, I do an action on my computer, someone across the world or someone watching sees this action happen. We have less than 1 second for that live end-to-end. We have less than 50 milliseconds of latency connecting to our servers. This less than 1 second is pretty good. This means that if I do an action, you'll see it now. So it's a little hard to have a conversation that way, but you can definitely have a synchronous social experience that way. And then 92% of our users are routed to the closest VPC to them. Again, there's always edge cases. There's people who have VPNs on or some strange setup, so it's not 100%. But most of these numbers we can attribute to, or the first and third number we can attribute to Route 53. Their features are great on this front. They're being able to notice how close out, which region I should go to, all that works great. In terms of reliability, this was a screenshot of our monitoring platform 1 year ago today. Well, this week. So this was November 2017. We had 20 different downtime incidents in the 5-day span. This isn't the full 7 days. That was 38 minutes of critical downtime. Critical here meaning that users were entirely unable to use our platform. This is a screenshot of the same metric over the past month and a half on all Stark-related infrastructure. We've had no downtime incidents due to Stark adequately provisioning for load. And remember, this is in addition to an 83% cost reduction, so it's not that it's just spinning up hundreds more servers than it needs. This is intelligent scaling. Talking more about that intelligent scaling, this is I believe it's a 3-hour period. In one of our busiest regions, we had 1,000 servers peak. This isn't users, this is the amount of servers that we have, and there's it's something like 20 users per server. So we have a little bit over 1,000 servers at peak in this one region alone. That's how we got to thousands of servers every day, as per the name of this talk, and 200 at the lower end. And all this scaling from that 200 lower bound to this greater than 1,000 upper bound happens in less than 20 minutes. So this is due to that velocity base. This is due to having those stopped instances. But this is proof that very quickly we can 5x our instances in a given region. And this more than, as you saw, 0 downtime, this more than adequately handles our case. Last thing I want to say is Stark, we use it for our video ingest. It's just a great tool in general. We'll be open sourcing it on our GitHub in the coming weeks. Check it out there, github.com/Bebo. Pretty easy to remember. We're going to be open sourcing it. Try it. Let us know if what you think. There's bound to be issues, but we want to make this a product that we can share with the community. Furkan had a few thoughts he wanted to share now. Give the stand to him.
Thanks, Johnny. So I just had some general thoughts around some of the things that we went through. So basically for us, software has replaced departments. Before Johnny started on ops, we had a traditional ops team kind of looking at servers. We previously had our own data center. And what we realized is if we treat most problems like software problems, we're able to kind of tackle them differently. And so we've taken a QA team, our ops team, and we've wrapped it up into software engineering, and we approach the problem in the same way. We create requirements, we put our code in GitHub, we tag it, we deploy it, we kind of have it go out, we can revert back, and pretty much across the board in every department in our company, in marketing and finance, we've put a software engineer there, and we've basically solved all problems as software problems. We find talent in unique places. So we found Johnny. Johnny, ran into one of our guys, was interested in what we're doing, spent time at our company. We have other people that would be non-standard hires at most places, and what we've done is we're willing to give people a chance. We have this concept of a green team. We basically, it's for a group of people that may not have the resume or the credentials, but they're really interested in startups, they want to build software, and I got started really young. I worked at a .com when I was 15, just like kind of Johnny, and for me it was just like, I was really passionate about this. I really just wanted to build things, and I don't know, you can find talent in unique spots, and for us it's more important to be passionate about what you're doing. You're going to get better output, you're going to be more interested, and you're actually going to go find the creative solutions that we need to scale up. Our team is small, we're less than 10 total engineers, and so each person is responsible for a lot, and they got to approach it creatively. And so when you find people that are passionate and really interested, and they really, really want to do this, and that to me is like, how do you get that person and put them in your company? And lastly, infrastructure has become ridiculously easy. I mean, Amazon, everything that they're releasing, everything that we're working with, it's no longer, hey, go get a rack, go buy a server, go wire it up. It's a couple clicks, couple buttons, and I mean, everything we've been able to put together is just, I'm constantly fascinated by how fast things have gotten. And I remember 10 years ago and how slow it was, and oh man, scale, and you're breaking, and you don't have the kind of resources, and now pretty much everything is there, and I would kind of go out and kind of find that. And so those are just my thoughts. I think Johnny wanted to finish it up.
Yeah. Last thing I wanted to say, this is my first conference that I'm speaking at. Tell me how I did. You can text this number if you want. Just give me some general feedback. You don't have to, you can. Keep in touch, and that's it. Thank you for listening to us. We're going to take questions now, I think.
You'll learn never to put your phone number on the screen again after that.
It's a Google Voice.
So we're taking questions. Hello? There we go. So we're taking questions through Slido. Are there questions up in Slido now? Here we go. Yeah, lots of questions. So, can you kind of explain how you're different than Twitch? How you don't do what Twitch does, you enhance the Twitch experience?
Yeah.
Can you talk a little bit about that?
Yeah, so basically Twitch, their goal is entertainment. You play this video game, you want to have other people watch with you and follow along your journey. What we created was recreational esports. Think about it like Little League or kind of intramurals, and right now esports has grown a lot, it's gotten hyped, and really they focused on the top, like the 1,000 pro players in the pro scene, and then you're playing the game. There's nobody in the middle. When you think about other sports like basketball, it's not NBA in your backyard. You have Little League, you have high school, you have college, you have intramurals, you have 24-hour fitness, you have rec leagues. So all of that is kind of what we looked at for esports. And our job is not for you to broadcast to thousands of viewers. It's you play competitively, and your opponents or your friends can watch you kind of compete in that. And so that's how we're different than Twitch.
Excellent. How do you synchronize players to play on the same game?
So we don't. We actually let you play whenever you want. The idea is you can play in your bedroom and you can start asynchronously. We use time shifting and kind of a little bit of intelligence around video and saying, okay, you started at minute 1 and you started at minute 3, and we're going to make it feel like it happened at the same time. And so we actually wanted everybody, to play on their own time and not have to wait around and say, hey, okay, are you ready? You're not ready. Are you ready? You're not ready. And we found out that this was one of the biggest problems of some of the other companies that were trying to solve the same problem, is organization, forfeiting, people not showing up, and we basically took all of that friction away.
EC2 is inexpensive, but 1,000 servers, that ends up can get costly. How do you monetize? How do you make money? How do you pay for this?
So we don't really make money today, but the company has a long history. So in the mid-2000s, Bebo was a social network that was like the MySpace of Europe, and it was sold to AOL for about 850 million, not 850 billion, that would have been a better number. But and Michael Birch, who started the original Bebo, set up our company as an idea lab where we get to construct a team and build different ideas. And what we do is, we get to come up with an idea, we get to build it and scale it, and try to get millions of users on it. If it doesn't work out, we go back to the drawing board. We keep the team together. We keep the learnings in-house, and we kind of keep going. And Michael funds the company, and our goal is to basically reach a mass of users and then figure out monetization strategies there. Currently, for this product, we're looking at a $10 a month subscription product, kind of similar to how parents pay for Little League. They'll be paying for this kind of organized esport process. So it'll be free to play, but then there'll be some opportunities to kind of get into different competitions and tournaments by paying $10 a month.
What stops people from just playing a video of Ninja playing a game and claiming those stats for themselves?
So gamers are tricky and they're sneaky and they try to do everything. We actually inject ourselves into the game, so we know what's running and what's happening. So we basically on the Windows clients and the Xbox clients, we get ourselves into the game and we can kind of see exactly what's going on and make sure you're playing the game. And we use computer vision and some machine learning for some anti-cheat items, so we can kind of detect abnormalities of gameplay and figure that out. And we have a very aggressive policy. We find if you're cheating once, you're off the platform forever. Got a nice big red button on our desk that we just press, so you don't want to mess around with us.
And what about orchestration for release deployments and rollbacks with Stark? How does that work?
So we have a small script that basically works with Stark. It's all using Docker. We use Docker Hub and tagging. So we roll out to a small percentage of instances. If we don't detect any abnormalities, we let it go to the rest of the instances. If we detect abnormalities, we basically pull those machines out of the pool and we add the next machines in place.
And your favorite game to play?
Currently on Fortnite and a little bit of Call of Duty, but historically probably FIFA or Madden is kind of where I've spent most of my time.
Excellent. Well, thank you very much. Please, round of applause for a great talk. In a few minutes, we'll have Robinhood giving some insight on their infrastructure, kicking off in 5 minutes.